Yes, several years ago, okay, it's not up to several years, it's about 10 months ago, I did a video and I said I was going to do the simulation in the next video. And yes, here we are 10 months later. And yeah, I've been quite had my hands full. So again, better late than never. So, oh boy, now it's lost. So in the video I'm going to link in description, we modeled the double notch hook coupler. And yes, I don't know how far I went, but then if I didn't already blend the edges, then you should go right ahead and do that. I think I did in the previous video. So blending the edges, so it's yeah, blending all of these edges, not this one though. So today we'll be looking at the simulation, or what I typically do when I have such a device as this. So we are going to be looking at the transmission properties. So I think this looks better. Yes, no, yeah. So we're going to be looking at the transmission properties of this device, and for that we're going to be specifying ports. So we're going to be looking at the transmission from either of these ports. However, what is interesting to me is the transmission of some particular modes from, let's say, this port to this port to a port up here, or from this other port to this one. Since the device is not symmetric, you wouldn't expect exactly the same transmission properties, and that's why it's important the orientation of this device when you finally put it on a cavity. So if you should put it in some other way, then you have really bad transmission, as we would see. So yeah, let's get right into it. So to get the transmission properties, which I think just yeah, the S parameters, the S parameters, yeah, the S parameter curves, yeah. Um, yeah, we would have to specify some ports. So we want to study transmission from one port to the other, so we have to specify the port. So I would select on this face, and then so what? Okay, Z. So what I did is F. I press F on my keyboard. I think I should find a way to get screen keycast. Yes. So either you press F on your keyboard, or you go to modeling and then you go to peaks and then you pick face. So it's the same thing. So I double click, and once I select the face, I go to simulation and waveguide port. Now I want to you could specify as many modes as you want in the waveguide port, but then and then the since this cross section is circular, you would expect to have your beam pipe mode. So what I mean by your beam pipe modes, for your circular or for your cylindrical waveguide or your circular cross section, the first beam pipe mode is the TE11, the horizontal polarization, then the TE11, the vertical polarization, then you have the TM01 mode, and I don't know which one comes next. I think it's maybe TE10 or something. But then you could look at you could pull up a chart and look at the modes that you're simulating. So for me, I'm mostly interested in the TE11 mode, which is the lowest frequency mode, and then the TM01 mode. So I'm going to put I want 3 port modes from here. Then I could also set the polarization. I mean, you could also technically not set it, but then I think CST automatically just picks 0 or maybe some other random. I haven't really checked to see if it picks some other random, but then my some other random and polarization angle, but then my best guess would be 0. So the polarization angle basically fixes the orientation of the T11 mode. So for the dipole mode, that you have 2 polarization. So a 0 orientation would be that the first mode would be 0, so like this, and then the second mode would be 90 degrees from it. So if you put a polarization of 45 degrees, then you'd have 45 degrees, your first mode, something like this. I mean, we'll see it once I simulate, so I hope I remember. And you would have your 135 degrees. So, and the angle also matters. You could do a study to see how the transmission properties change when you change this polarization angle. the angle, the orientation of the polarization angle of the modes for the dipole modes, and also the quadrupole modes. For the monopole mode, since it's azimuthally symmetric, you don't really have any difference, so it's the same. But for the dipole modes, depending on the angle, the polarization angle you put, you have different transmission curves. So I'm just going to leave it at 0 and then 3 modes, and that's okay. Yes, and then for the second port, so let's say this is port 2. The same thing, F, select phase, go to waveguide ports, and then, okay, that's if it would show up. Why is it taking so much time? Okay, and 3 modes, and I don't really know, not really sure what shielding does, but I think CST turns it on anyway. I mean, you could look at that in the help, but I have never really had need for it, so I have never checked. Yes, and also check your port modes to ensure that it's pointing away from the port, so inside of towards the geometry. I think sometimes there are some ways you could define your port and then it points outward, but then you wouldn't have any signal into it. So make sure it's this way. By default, it should be, but if anything goes wrong and then you do not see any transmission, then you should pretty much check your port mode that the direction is pointing inwards. So yes, that's it. And then so what we're exciting at this port are the waveguide modes, which are your TM, your TM modes. But then at the top we have a coaxial line, so you have your TEM mode, and it's just one, right? You don't need to. So if I should go to F and waveguide modes, it's just your TM mode, so it's just going to be one port mode, so number of modes one, and then there's no need for any polarization because of the take your TM mode. So I think we're done. Yes. So that's pretty much it for the setup, and then yes, that's pretty much it. And in case you hadn't changed your setup solver type, we want to simulate this in frequency domain. So you'd go ahead and change it to frequency domain. And if your problem type is anything different than other than high frequency, then you could change your problem type from here to high frequency and change this to frequency domain. So let's go to specify a frequency range. So for this device, now I can't remember if it's for a 400 megahertz cavity or for a 800 megahertz cavity. Now, remember that the whole essence of this coupler is to dampen the impedance of some higher order modes. So if this is for a 400 um, megahertz cavity, then we are interested in the range, maybe between three. I mean, also depending on the cavity, but then 300 to 700, I think it should be okay because your couplers are specifically designed for narrowband. Your coaxial couplers are most of the time designed for narrowband damping, most especially. But then you could also have broadband damping, but not very good. But you could also have broadband damping for the couplers. But then this for your hook coupler, it's specifically designed for narrowband damping of some of the um, higher order modes in the first dipole passband. So and then remember the second, or I don't know if I mentioned it in the last video, but then the second purpose of your coupler is while damping these higher order modes, it should not also dampen the fundamental mode because it's like you're putting energy in your system and you're removing it. So you also want to check for the rejection of the fundamental mode. So you should have very low transmission for your at your fundamental mode, which you'd see as a notch. And this is a double notch coupler, so you should see double notches um, around the fundamental mode, which I think, I mean, if I remember correctly, for this um, coupler, it's 100 megahertz cavity. So yeah, that's okay. And then make sure to put your background to PEC. Yes, if it's not the default, and then the boundary conditions, electric, and then open on the Z. Yes. So that's that. Z min and Z max open, and hmm. Y min is yes, but I think Y max. Wait, does it make a difference if I should change this to open or leave it as electric? Is it electric ideally? Hmm. I think so. I'll just leave it. But then you could also check. Now I just thought about this right now. I think this is how I always simulate it. But then I just wondered if I change this to open, if it makes any difference. That's the Y max to open boundary condition. If it makes a difference, you can check at your own time. But yeah, this is how I normally run the simulation. So let's see. I mean, I can't really think of what exactly it would be right now. So that's pretty much it for the setup. Now for the setup solver, we go to, I mean, you could use the general purpose, but then mostly it's fast to reduce other model. It takes shorter time. And so the source of my excitation, you could select any of these ports. So it could be port 1, port 2, and then you have the number of modes you specified available. So you could also specify also it excites all of these modes and then gives you transmission properties. But then what I'm mostly interested in is the transmission from either 1 or 2 to 3. So instead of exciting 1 or 2, I'm just going to excite 3 because also it has one port mode. So no, sorry, 3. And it has just one port mode. And depending on what you're looking for, you could also specify how much you could also specify some, maybe you're interested in some particular frequencies. You could also specify the value here. So you could change it to single and then specify some frequency that you're interested in. I think somehow with the fast reduce other model method, it kind of gets more accurate around these frequencies that you specify. Turn off adaptive mesh refinement is going to warn us to turn it on, and I think if you haven't done a convergence study, then you should turn it on so you are sure that your results are accurate. But yeah, that will take time. So we're going to leave it there. Then specials, you could change the accuracy to whatever accuracy you want. You could also change to whether iterative solvers or direct solvers. I'm just going to leave it as automatic, and yeah, and the rest of the simulation, the parameters still the same. And yeah, simplify model, haven't had need for this. Yes, and that's it, and we are ready to run our simulation hopefully, and also the mesh tetrahedral. Start. So I'm going to this shouldn't take. Oh, I didn't check my mesh I didn't check my mesh my global parameters for mesh that should appear here any moment from creating the mesh. Okay, 54,000. It shouldn't take much time. I don't know if I should pause. Okay, I'll just pause and then when it's done I'll come back. Okay, so that's done. I think it took maybe less than 2 minutes. Yes, I think it took less than 2 minutes, and then the accuracy, of course, I didn't make it very accurate, so yeah, it took less time. So yes, we have our results, and we view our results in. Why do I have to do? Okay, now first you could view the port modes. Now if we should view for mode 1, now remember what I said about the polarization. Okay, zero polarization is this. So this is the first, this is the T mode, and then you could also calculate this. I think the dimensions for this should be 150. You could also use the formula to calculate to see that the cutoff frequency for this geometry, for this radius is 585.737. You could calculate it to see. So this is your TE mode. Here you have the information about the mode, your TE mode, the cutoff, and then the accuracy of the calculation of the mode, because then it calculates the port modes first. So the accuracy is 6 to minus 13, which is very good. And mode 2, you see that is just 90 degrees polarization, right? And then you see that these make a different angle with the hook, the part of the hook that is dipped into the cavity. So I mean, you would also expect a difference in in the transmission properties as you rotate through this angle. So you would see first of all that the 0 degree and then the 90 degree, which is modes 1 and 2, although the same TE mode with the same cutoff, they have different transmission properties. Then the third mode is the TM. So I think I'll view the H field instead. So it's the TM01 mode of your circular cross section, and then the cutoff is 765. Oh, my camera is gone off. Okay, it's back on. That's weird. Or maybe not weird. I mean, I don't know why it happened, but then it happens. Yes, so this is the TM010 mode, TM01 mode, not 010, and then you could check that the cutoff is this. So we have these three modes, and then if you should look at 6, no 3, 5, no 8. Yes, maybe you should look at port 3. I mean the same thing you have in port 2. So if we should look at port 3, you have your TM mode. Yes. So and then your H also. So yeah, this is what you have at port 3. So these are the port modes. And then to view the transmission properties, we go to 1D results and then S parameters. So you have these different plots. So yeah, from this plot, without knowing, I mean, what this means yet, I'm going to get into that. We see that for this mode, okay, I think I'll just explain it. So you have S1, 1, 3. So this represents the port numbers. So the one outside of the bracket represent the port numbers, and then the values inside the bracket represents the mode. So this is read as the transmission from port 3 to port 1 of the first mode. So it's, I mean, the way I try to think about it is what part of mode 1 excited. I mean, you just have one mode in port 3. So what part of mode 1 excited, what component of that does is the mode 1 at port 1. So now you know you have your electromagnetic waves, and they could be decomposed into different components. So your multiple components, they could be decomposed into different components, and then they are just a linear combination of these components. So you have that the electromagnetic wave going from the excitation of mode 1. I mean, it's just one mode, but then let's say mode 1 at port 3, it travels through your device, and then as it's traveling, it's interacting and then changing form. But then you could decompose this into mode 1, mode 2, and mode 3 at port 1. So it's like what part of this, what part of what amount of this component, so mode 1 component, which is your T component, goes through port 1. So it's actually your S13 parameter, but then for mode 1. So, and then you also see that this is mode 1. So mode 1 traveling through the structure, I mean, it interacts and then changes form and everything, and then decomposed into what component of it is decomposed into mode 2 at port 1. Yeah, it might be a little tricky to get around, so maybe just take some time to think about it. You have first mode, I mean, it's just one mode, but then you could have mode 2 or mode 3, but then it travels through a structure and then it has like different forms, and then you could also still decompose it into these components. So you could decompose into your T11 plus T11 horizontal polarization plus TM01 plus other modes, right? So that's just what this is, and then you also have what component of the mode 1, which is the wave that you excited at port 3, what how much of the TM01 is inside of this, so at port 1. So what you see is you have the transmission, and then where you have a notch, it's you have a rejection of that mode. So the deeper the notch, the less transmission you have. So it looks like a singularity here. So you have that it's rejecting, let's see, the minimum, it's rejecting the T11 mode at 400 at 406 megahertz, and then you have this transmission. So this is the place of maybe maximum transmission. So you have transmission at 494 megahertz, and you also have good transmission at 627. Between you have maybe a fair transmission, and yeah, that's it. So um, for me, I am usually interested in this transmission. I think yes, either this, so this and this. So now you see, you remember that mode 1 and mode 2, they're exactly the same mode. At port 1, they're exactly the same mode, but then with 90 degrees polarization. So you see that your transmission properties are quite different. I mean, if you should look at it somehow, this value is okay, a bit lower, but around this part you have similar transmission, but then the values are greatly different. So you see that it transmits the zero polarization, if I'm correct. Yes, the red one is the first one. It transmits the zero polarization of the T11 mode better than the 90 degrees polarization. So the 0 degrees polarization better than the 90 degrees polarization. You could have 45 degrees, 60 degrees, and then you could actually do a sweep over this angle and then look at the difference of which one, in which polarization you have the best transmission. Then the other one I'm interested in my work is the TM01 transmission, the TM01 mode, which is S13. Remember the port 3 mode is TM01. So this is what I'm interested in also. And then I am not interested in this broadband part. I am only interested in this. I mean, maybe not exactly broadband, but yeah, narrowband, this higher order modes part. I'm only interested in this part where you can see the double notch. So this effect that you have of a double notch. Now I want a rejection, a very good rejection at 400 megahertz, right? If I had a single notch, then you could already imagine that this is really sensitive to perturbations in the geometry. And then a slight change might shift this, and then you go from, let's say, minus 140 or something dB to maybe minus 95. I mean, still not very bad, but then you see that this already has it's less sensitive because of the double notch. And if you should maybe, so this is supposed to be for around 400 megahertz, so maybe a little perturbation, you are still around minus 111 dB, and then a little perturbation to the right, you're still around minus 111 dB, so which is good. So that's the essence of the double notch coupler. And then I think I've mentioned that I'm interested in the TE11 mode and then the TM01 mode, but then I haven't really explained why. So I'll show you a typical plot of, um, okay, maybe focus on the, which one should you focus on? Okay, anyone, but then I'm focused on the orange plot. This is actually for a cavity, CPC cavity, which is for the lepton collider that yeah, that I think it's to be built in China. Yes, yes. The so you have the FCC, which is built by CERN, and then the CPC. Now I don't know what this means. The acronym means again. So if you focus on this, right? So this is the fundamental mode, which is at a 400 megahertz. So this is the mode we want to. This is the mode we use to accelerate um, uh, particles. Now, every other thing you have is the higher order mode. So this is the longitudinal higher order modes plot. So you have that the first higher order mode is the TM011 mode. And what happens is that the TM011 mode couples to the, oh, I do not have a cavity. I think I should look for a cavity. Okay. So maybe I think that would, maybe I'd open cavity geometry. Okay, got one open. So in the end, what we do is we couple this. So this is one of the couplers you're seeing. So we couple this coupler in the end. We couple this coupler, or we assemble this coupler in the end to the cavity geometry, right? And then what happens is that we want our fundamental mode, which is a TM010 mode for this case, to resonate inside of the cavity. So what I said about damping now, if you put an antenna here, which is this coupler, you see that there's a possibility for this to also pick up the fundamental mode, which we want to be confined within the cavity, which is why we want such transmission. Now, what happens is that the higher order longitudinal modes, I mean, I'm going to only speak about T M011 mode. Okay, these are so many terms that I'm using. Just know that the higher order longitudinal modes couple to the longitudinal modes of the beam pipe. So the first higher order longitudinal mode couples to the TM01 mode of the beam pipe, and that is why I'm interested in the transmission properties of the TM01 mode of the beam pipe, right? Because once the higher order mode couples to this, I need to, oh, also your fundamental mode also couples to this TM01 mode. Your fundamental mode in the cavity is TM010 mode, and it couples to the TM01 mode of this of the beam pipe. So I want to see how well this coupler can reject this this mode. So that's why I'm interested in the properties around here. And then looking also again from the plot. Oh, this is for longitudinal. Okay, I need to get the transverse impedance plot. Okay, pulled it up. And so for your transverse impedance, I am mostly interested in this. I mean, the goal of designing this particular type of coupler is to be able to dampen the modes in this first dipole passband, which you see here. So these modes couple to the TE11 mode of the beam pipe. So that's why I'm interested in the TE11 mode for the transverse transmission. So I want to transmit this mode. So I need really good transmission around, let's see, maybe about 480 to maybe 500 or 600 megahertz. I need really good transmission, and then you could see some peaks. So I mean, in an optimization, I would optimize the maximum transmission, which are these values, to these peaks, to these peak frequencies. So yes, so that's why I'm interested in the transmission properties of the TE11 mode and also the TM01 mode. I feel that there's a lot of information for maybe someone that is not, I mean, in the field. So apologies for that, but yeah, I couldn't find a better way to explain it. So yeah, that's pretty much it. And then you could also look at to port 2, so the transmission properties to port 2. Now remember when I said the transmission properties, so if we should look at 1131 and then for port 2, 2131, okay, it's exactly the same. But that's odd. It should be different. Or maybe it's exactly the same for the 0 and 90-degree polarization, but then different for others because this coupler is not, yeah, it's not symmetric. You have different, so this way and this way, it's not, is it supposed to be? No, I don't think so. I mean, but maybe for the 0 and 90 degrees, it's the same. But it's not always the case that the transmission from 3 to 1 is the same as 3 to 2. I don't know, you could also check for 45 degrees and see, but then it's not always the case that it is the same. Yes. So, yeah, that's basically it, and yeah, I hope I didn't miss anything. So, okay, maybe in the next tutorial, I hope it's not 10 months again. I show how to actually optimize this. So you could optimize this by changing the parameters, by playing around with the parameters. You see that each of these peaks or this trough, which is the rejection, changes when you change some certain variables, and then the goal is usually to move these peaks to these values that we have here. So I determine my high impedance frequencies and try to tune this coupler such that the peaks are at so this is at 494 megahertz. So I think for this optimization I might try to get this from 625 megahertz to maybe 545 or 550 megahertz. So that's one of the goals, to get these peaks to align at the frequencies of the with the highest impedance. But then the second goal is to make sure, or to try and get the peak to be broad, so not to be sharp. So you want something like this, because sharp means it's really sensitive to perturbation. So any little perturbation, it might go off, and then you have like really poor transmission. But something like this, which is not very sharp, is usually desired. So one goal is to get the frequencies to, I mean the peaks to align at the frequencies of interest, and then the second is to try and broaden the the curve around the peak, so you do not need sharp edges. So yes, and this is not part of it. This is an artifact. I don't know. I think there's a resonance around this. There's a resonance of one of the components around this point. So this does not move even if you should change the properties, if I'm correct, if I remember correctly. So basically that's it. And for a typical hook type coupler, you would only see one of these notches. But then this was a double notch hook coupler. So I mean the what brings about the double notch is this other component that we place between the regular hook type coupler. So yes, that's it for the video. I hope it wasn't so technical, and yeah, you could always ask questions below. I'm not I usually do not receive notification from YouTube that I've been asked a question, so and then I hardly go through all the videos to check the comments, but I'll try as much as possible whenever I see the questions to respond, and I hope I get less busy soon, so I could, yeah, maybe make more videos, and also yeah, respond timely to questions. And yeah, until then, see you.